Hello, welcome back. Today we're going to take a look at limits continuing. But today we're going to really focus on what happens if the limit of two functions exist. So we're saying that the limits of two functions exist. And it's very simple. If the limits must exist, then it means they are numbers. And as a result, we can actually apply all our algebraic operations. And that's what this says. If the limits of two or more functions exist, we can treat them all. That means all those algebraic properties apply. And that's what this is saying right here. For example, if the limit of f is L and the limit of G is M, again, we're told that the limits are certain values, so we know here that the limits must exist. We can add limits together. So if I'm looking for the limit as x approaches c of f plus g, I can just add their limits together. So likewise, we can subtract limits. We can multiply limits. We can divide limits, provided we're not dividing by 0. We can multiply a limit by a constant, and we can even raise limits to a power, again, provided we're not dividing by 0 and we're dealing with the real numbers, not imaginaries. That makes things complex. Hope you see what I did there. We can also take the limit of a composite function. If f, and this is going to be discussed later, okay? That's going to be discussed later. If f and g are functions such that the limit of g is L and the limit of f approaches f of L, then we can say that the limit of the composite of f of g is f of L. Again, we're going to discuss this one a little bit later. Okay? But right now, all we're really doing here is we are just applying our limit rules here. So here's what we have. We're told the limit as x approaches f is 2, and the limit as x approaches a of g of x is 3. Find the limit if it exists. So for the first one, this looks like my constant multiple rule. So if I want to think algebraically, this is really saying 5 times the limit as x approaches a, of g of x. 5 times, well, as x approaches a of g of x, well, we know that that's 3. So that's really just saying 5 times 3. So this we know is going to be 15. Now, you don't have to write all of this out. It does help, but you don't have to write that out. If we look at part B right here, again, I'm not going to show all the same work here, but what I want you to know is, if we look at this one, the limit as x approaches a of 6, well, this is kind of weird. If I think the limit as x approaches a of 6, well, 6 is a constant function. It never changes. Think about that. This is basically saying y equals 6. And if I look at that, y equals 6, if here's 6 and here's a, well, that limit is always going to be 6. So this never changes right here. So this 6 is always going to be the same, just 6. As x approaches a of f, well, that's told as 2, and the bottom, g, is 3. Now, I am okay if you leave this answer. The AP is okay. They say don't simplify, okay? Because I cannot tell you how many people miss that all the time. But if you want to, this is just 8/3. And there's our final answer right here. So let's see if we can do part C. Now part C, if you notice, is saying it says f of x squared. That looks like my power rule. So on top here, the limit as x approaches a of f, we know that that's already 2. We're just going to square that over g of x. Well, g we're told is 3 minus 3. So what we wind up with is 4 over 0. And you can't divide by 0. This is a big no-no in mathematics. So this answer for now is just D and E. Does not exist. Okay? Never leave 4 over 0. You will get that wrong if you leave it like that. You have to know that that is a value that does not exist. And notice I don't put undefined. I don't put no solution. I'm using that does not exist. So basically just as we can do algebra here. Now we're going to talk about how we solve limits of actual functions. of a graph, without a graph. So these are without a graph. Whoops, can't spell today. Without a graph. The easiest method is what we call substitution. Now, a substitution is not really a method. All we're doing is we are just going to see if the value exists. So that's what this says. The easiest method for checking if a limit exists is to check to see if the value exists. Because if the value exists, the limit must exist. And it's easy to see. If I have like y equals x, if I graph that function, whoops, totally messed it up. Notice at x equals 3, does the value exist? Yes. Does the limit exist? Am I approaching the number from the left and the right? Yes. So the limit and the value are the same. And that's the substitution method. We are going to assume that the limit is the same as the value until it isn't. We'll talk about that in just a moment, okay? So you might recall yesterday that if the limit equals the value, this is really what's called a continuous function. You might remember that from yesterday. So if we take a look here, if I want to check the limit as x approaches 3 here, well, the first thing I look here is at the bottom. What's the one thing x cannot be? -1. The only thing you can't do in math is divide by 0. So we know x can't be -1. So I know that the only spot that this may not be continuous is -1. And you might remember that last year that this would be a rational function. That would be an asymptote at -1. So I can use my substitution method. And what that means is all I have to do is I'm just going to check if the value exists. So I can just go 2 times 3 minus 5 over, plug in the 3. Everywhere there's an x, I just plug in 3. 3 plus 1. And that becomes 6 minus 5, which is 1/4. So does the value exist? Yeah, that's my value. It exists. So therefore, I can say that the limit as x approaches 3 of my function, just don't write out this, just use f of x, is 1/4. Because the limit, the value exists, the limit will also exist there. And again, it comes back to that idea we talked yesterday about continuity. Remember, we're going to talk a lot about continuity this year. So because x can't equal -1, that's the only spot we have to worry about. 3 is not -1, so I can plug it in. Now notice how I wrote my answer. I'm using that notation. The limit as x approaches 3 of the function is 1/4. And if you've never seen these little 3 dots before, that means therefore. Mathematicians are very lazy, so we tend to write little things in short form. That means therefore. So let's try number 2. Number 2, you might recall, is a parabola. Now, is there anything that could cause this to be is there any issue here? Can you think of anything that x cannot be? Like right over here, x couldn't be -1 because you can't divide by 0. And you can't. So I can use my substitution method, and I just sub in my -1. And this becomes -1 squared minus 3 times -1 minus 4. And of course this becomes 1 plus 3 minus 4, which is 0. 0 exists, so the value exists, so therefore we can say that the limit as x approaches -1 of our function is 0. Now notice again, I just used f of x. The AP is okay with that if you just want to call that f of x is 0. So take a minute if you want to and pause and try number 3. Oh, Triggerlicious. I can plug that in. What is the sine of pi over 3? Oh no! What's the sine of pi over 3, right? So we should know that one. That is what? Root 3 over 2? I hope I got that right. So therefore we can say that the limit as x approaches pi over 3 of our function is root 3 over 2. So these are all based on the fact that in this case that the limit will equal the value. We're going to assume it's continuous until it ain't. Now, but the next question says, well, what happens if substitution fails? We have what's called the indeterminate form. We're going to talk a lot about indeterminate form throughout this year too, so it's going to be a word you're going to get used to. If we try the substitution method and we get one of two choices, 0 over 0 or infinity over infinity, This is a huge problem because we don't know these values of the two fractions. And the reason we call it indeterminate, well, because indeterminate means I don't know what it is. Indeterminate is the ultimate, I don't know, or IDK, right? We don't know what this means. For example, let's deal with 0 over 0. Well, I know that 0, any number divided by itself, has to be 1. But I also know that any number divided, 0 divided by any number has to be 0. But I also know that any number divided by 0 does not exist. It's asymptotic. So for 0 over 0, I have three choices. 1, 0, or I don't know. So that's why we call it indeterminate. So we don't know the values of these two fractions. That's why we call them indeterminate. Now there are a lot more other forms we're going to talk about later on. If we try the substitution method and we get one of these, we have to come up with another method. This is where the substitution method fails. Okay? And we have to try another method. And let's take a look at it. And the method we talk about is what's called the factor cancel method. So I'll tell you what, we're going to pause right here for now. So what I want you guys to do, go on to lesson number 2, and we'll take a look at the factor cancel method and the conjugate method. Okay? See you soon.